Okay, here we have worksheet 4 we're going to go through, and the first thing I want to say is that I actually messed up and didn't. These electron donating groups, electron withdrawing groups do stay here. They don't disappear, and I apologize for that. Rank the following reactions in reactivity from most to least. So I'll let you refer to your notes as to how to make the electrophile, but let's just assume we have the electrophile and go through a quick mechanism of how this reaction happens so that we can judge these a little bit better. Right? And then you can just use some base. I know I used a different one. In discussion, but any base works in this. So that's the basic mechanism, right? Now, if I just say that this is A, right? So for B, if I put an electron donating group, and let's use an example and say, we'll do it over here. Electron donating group equals methoxy, right? Methoxy is a great standard electron donating group, right? What would it do if I had a methoxy group? Right, so I'm drawing in a different color so that I don't have to redraw all the structures and go a little bit quicker. Right, well, obviously what it would do is that this is the important resonance structure I want you looking at. And you're gonna have a lone pair here that will donate and make an additional resonance structure, right? This makes the intermediate more stable, which makes the reaction go faster, right? If I draw the corresponding one, this corresponding one, sorry, with an electron withdrawing group, use nitros or an electron withdrawing group, what you see is you put two positive charges next to each other. That's bad. That raises its energy. So the way the energy diagram would look for this is that you would have A, which would be in blue. You would have C, which would be bad, higher in energy. And you would have B, should be lower in energy. Right? So the way the reactivity go will be B is greater than A, which is greater than C. That's the way the reactivity would go. Draw the mechanism for the following reactions. Oh, okay. So first we gotta generate our electrophile. Get that, and then is this focusing all the way down? Yeah. We need to color it a little darker or something. Then you can have benzene come and attack. And then finally, you can get your final product by having chloride come in and deproton. That's how you get this. So this is basically the same as FeBr3, but it just uses chloride instead. The exact same mechanism. Okay, for this one, on that, we'll have chloride as our base, because when I made this worksheet, we had not done Friedel-Crafts calculation yet. So that's going to be our base. Our first structure is going to be this. And then chloride can come in, grab that, and get there. There are two res structures, just like there are right here too. Yeah. So just keep that in mind. I'm not drawing them, but they are there. All right, predict the product. So for this one, this really depends on how well you know your hydride shifts. So this is going to be the first one. Let me get this, that hydrogen moved over here. I want to change the color of the next proton just to keep it a little bit easier for people to keep track. Then you're going to have benzene attacks, so the final product you'll get, I'll draw this in red, will be 1, 2, 3, 5. 1, 2, 3, 4, 5. That'll be your final product. Here, the alkene's going to be way more reactive than the benzene rings, so you should get this. Now I have a carbocation, the other benzene ring can attack it. Yeah, I'll do the mechanism for this, why not? Is it all on the page? It is kind of on the page. So one of these is going to be full. So it's going to be like that, and then finally we'll have some sort of base come in, and I'll change the color because it's going to be a crazy arrow. Coming like that, and we will get our final product. Getting this. Okay, we didn't really do directing effects, so if you struggle with this last one, it's probably not that important for the exam. But if you look by resonance, there are 3 positions of the nitrogen lone pair donates electron density. Ortho, 2 orthos and 1 para, right? So the way this is going to go is, as you do the reaction, I'm going to use a different color for my actual reaction arrow. Let's pretend we already generate our bromonium ion. Right, you get an extra resonance structure from the lone pair, so I've been doing those in red. Three resonance structures, right? Yeah, I'll show them just on the. I'll show the arrows for, or how you make 2 of them, right? You're just doing a cascade of arrows. You could have just had this one come over there if you want. This makes the ortho product. right? If I want the para product, let's start with this. Again, you will have 3 resonance structures. And you get that. Okay, you only see ortho and para, explain why. So it does say draw a mechanism. I'm gonna say just explain the phenomena, use structures if necessary. Because I think that actually makes more sense. So I'm gonna draw, if I put the bromine at all 3 positions. Let's look at this. Right? Now, which positions would the positive charge go to in the ring? They're going to be these positions. Right? The lone pair and the oxygen can stabilize ortho and para. So the lone pair and the oxygen can stabilize the orthopara intermediates via resonance, which favors the orthopara products. So that's the reason why the para product measured being greater in abundance than the ortho product. Explain why. Sterics. It's really just as simple as that. It's a sterics thing, right? Remember, okay, I should say this. There are 2 ortho positions, and there's only 1 para position. So there are 2 ortho positions and 1 para position. You would think statistically you would get twice as many orthos as para, unless there is some directing effect. And the directing, or the thing that's controlling it, is sterics in this case. All right, for this one we have electron withdrawing group or a nitro group, and you have a meta director. So again, I'm going to just draw the 3 different intermediates.
Here you go. Are you so excited? Here we go.
Yeah, so if I look at these, where's the partial positive charge go? It's going to go in these carbons. Right, and what we see is that in the meta, the positive charge never gets here. Remember in this nitrogen, in the nitro group, right? There's a positive charge on the nitrogen. So these 2 positive charges being next to each other is bad, right? So that's why you get this. So positive charge on nitro group favors, maybe disfavors OP more than meta. So meta is major. product.
You want orange now? Sardines.
Right. So it's not really that the nitro group makes the meta product better, it just makes it orthopara worse than meta. So that's why you get meta as the major one. Which benzene ring, methoxybenzene or nitrobenzene will react faster? This will be methoxybenzene. Remember, the methoxybenzene is donating electron density. Nitrobenzene is withdrawing electron density. You want that benzene to be nucleophilic, so you want as much electron density as possible. Okay, let's count the electrons for aromaticity. 2, 4, 6 electrons. This is aromatic. It's 2, 4 electrons, non-aromatic. 2, 4 electrons, non-aromatic. 4 electrons, non-aromatic. 2, 4, 6 electrons. This is aromatic. It does not matter if those methyl groups are there. Right, still aromatic. A lone pair. 2, 4, 6, 8 electrons, non-aromatic. 2, 4, sp3 hybridized carbon. This is definitely non-aromatic. 1, 2, 3, 4, 5, 6 electrons or aromatic. Right? Remember, this is the trick for nitrogens and heteroatoms for their lone pairs. If the nitrogen is or oxygen is making a pi bond, its lone pair cannot participate in the conjugation for counting for resonance. If it's not making a pi bond, then you do need to count it, right? So this nitrogen lone pair has to be counted because otherwise it's not sp2 if you don't count them. So it has to be counted. So that's like the shortcut to it. So if pi bond on heteroatom, don't count lone pair. If no pi bond on heteroatom, count lone pair. All right, molecule 1 reacts much faster than molecule 2. Explain why. So remember, if we're talking about these actions as acids, we're really saying this is much more stable than this. Why? Well, you count the electrons. This has 8 electrons. This has 6 electrons. So this is aromatic. This is going to be non-aromatic. So I guess if I was being super careful on an exam, I would say molecule 1's conjugate base is aromatic. Molecule 2's conjugate base is non-aromatic. Therefore, fuel 1 reacts much faster. Yeah, so we did that. All right, last question. NMR piece. So you don't actually have to worry about this on your exam, apparently. That's what I've been told. But I'll still do this just because. So this is assuming simple splitting. Right, and by simple splitting, this is like a doublet, a doublet, a triplet, doublet, doublet, singlet, doublet, doublet, triplet. And you can probably figure it out from here. The most important one is that you can tell the para-substituted benzene ring. And that's going to be this. So this is molecule A. Right, this one theoretically should be doublet, triplet, triplet, doublet, singlet, doublet, triplet, doublet. So you can see that this is C and this is B. If it's not simple splitting, these would be super hard to tell, except that molecule B, spectra 2 or molecule A, the pair substituted one, always will be a pair of doublets. Always, 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 because you have this nice line of symmetry here. So you should definitely be able to recognize that. All right, that's the end of this worksheet. Good luck studying for your exam.